Hi, my name is Brandon Deloso, and I'm here to talk to you today about ketone reductase biocatalysis and the synthesis of chiral intermediates towards generic active pharmaceutical ingredients by the people you see here. The purpose of this article is for the researchers to demonstrate the versatility of biocatalysis using ketone reductases, which are allo-keto reductase enzymes that catalyze the reduction oxidation reactions of ketones and alcohols to make chiral alcohols, which is the enantiomers they're looking for. Montelukast, which is a well-known drug that was synthesized organically and is now synthesized using creds, is a very known example of this. Originally, during the organic synthesis, it needed a powerful and expensive reducting agent known as dip chloride. Seeing as how it was no longer needed with the cred, the synthesis is now cheaper and more sustainable in the long term. The researchers for this paper also made it very clear that their goal is not to have perfectly optimized reactions for this. They were just trying to get the optimizations they needed so they can get the results to prove that creds can actually work in replacing organic synthesis. So the interest in the patents ending soon comes from older drugs not having the access to the biocatalytic pathways that are available now, so they can take a look into the new ways of actually synthesizing these drugs to have a more sustainable long-term manufacturing process as well as less environmental factors. Some major long-term benefits of the biocatalytics is that it is more likely to produce a more sustainable manufacturing process for efficiency, environmental burden, and energy usage, especially since active pharmaceutical ingredients are at a higher value right now. Here's a list of the generic drugs they had used for this project. 8 total active pharmaceutical ingredients were chosen: a prepitant, an antiemetic, a tasnavir, which is antiretroviral, crisnotinib, an anti-cancer drug, indacaterol for COPD management, montelukast twice, which is for asthma. I do not believe number 6 is montelukast. I believe that is a typo and is actually another experimental drug. Then there's ticagrelor, which is for thrombosis or blood clotting, and then vilanterol, which is for another COPD management drug. So the reason they had chosen these drugs is for their vast structural differences, and they believe that since the structures of 8 of these are vastly different, they figured that'll be enough variation to assume how other ketones could work with it. So for the experiments they performed in this paper, there were 3 of them initially: the initial enzyme screening, the optimization, and the scale-up. For the initial enzyme screening, there are 2 different procedures used initially, but one was ultimately deemed better. For this, the purpose of this was to prove that the reactions actually occurred, and they can go into further detail with looking into the experiment conditions and everything else with it. The optimization has to do with the temperature, the pH, the concentrations, in order to make sure that the experiment can actually work later on. Scale-up is for industrial manufacturing later on down the line, when it actually gets to that. The researchers wanted to see if they could actually manufacture these cred products on an industrial level using up to 1,000 milliliter scale. And on the right, you'll see the reaction in which cred exchanges NADPH and gives a chiral alcohol from the ketone. And then you can see in the bottom the reverse reaction, IPA to acetone, which is a part of the second procedure and is rather important. On the bottom part of that, you can see another part of the procedure, which involves the glucose dehydrogenase enzyme as long as glucose and glucolactone for the recycling of the NADPH. The initial enzyme screening is based off a 96 well plate format and visualized using a standard colorimetric NADPH sensitive format, where a red color is indicative of a positive response. The aqueous solvent consisted of potassium phosphate, magnesium sulfate, NADP+, NAD+, D-glucose, glucose dehydrogenase, the ketone, of course, and the cred. It was also reacted in a 9:1 aqueous isopropanol mixture, which is not the most optimized one, but I'll go into that later when I get to the optimization, as well as 30 degrees Celsius it was ran at and pH of 7. Also, for assays, it was taken. They were taking out 20 microliter aliquots at intervals. We don't know how long because they didn't tell us. Diluted with 800 microliters of acetonitrile for the LCMS or 800 microliters of methanol for the GCMS. The aqueous solvent for the second procedure was really similar, just subtracting a couple of things like NAD+, the glucose, and the glucose dehydrogenase. It was all reacted the same way with a 9:1 aqueous isopropanol with 3 milliliters of that, 30 degrees Celsius, and a pH of 7. Also, for testing, 20 microliter aliquots were taken at intervals, diluted into 800 microliters of acetonitrile for the LCMS again, or 800 microliters of methanol for the GCMS. And from these screenings, they were able to determine that 5 out of the 8 ketones had reacted to produce the enantiomers they were looking for. Initially from the assay, the researchers confirmed that ketones number 1, 2, 6, 7, and 8 all had a positive red response from the well plates. Now, that indicates that either the enantiomer they were looking for was made or both enantiomers were made. Now, the researchers were looking for one enantiomer specifically, however, other enantiomers, like from ketone number 1, can be used in further reactions to produce other clinically proven medicines. Now, ketone number 3 did not initially react, the observers noticed, but they then reacted it with a modified CRED from alcohol dehydrogenase. They did have to extensively modify it so it would work, however, it did work in the end, which proves that CREDs are very versatile and can be used in multitudes of ways, as well as with optimization in order to assure that the ketones can react. They also ran a bunch of well plate reactions without adding the CRED. They ran the IPA cofactor recycle and the GDH cofactor recycle. They initially thought that the GDH would have the most background reduction, my mistake. However, they noticed after running the assays that there was no achiral background reduction from the GDH as well as from the IPA, which is good news, meaning there won't be any excess reactions going on. Based on the enzyme screening they had used previously, they had determined that ketone numbers 1, 2, and 7 were the best 3 to use to optimize and scale up the reaction due to the conversion in high EEs in both enantiomers that were produced. The figures I am showing for this slide were all used in order to find the loosely optimized conditions. For each condition, they needed to find each different setup unique for it. So, for the first graph I'm showing, it is for the IPA solvent composition. Researchers noticed that enzymatic activity greatly decreases if the isopropanol concentration is above 40%. From that, they noticed ketone 2, which had the lowest solubility in isopropanol, reacts best in 4:1 concentration of water to IPA. This is important to figure out beforehand due to the cofactor recycling that was needed to occur, so they had debate between the IPA and NADPH as well as the GDH and NADPH. IPA was chosen due to the cost performance of it as well as for solubility issues that will be spoken on later. For the next one is the pH tolerance. Ketone number 1 was chosen for this one. They don't say why, but they tested it in a range of pH from 5 to pH 8.5. They measured the conversion every 2 hours to allow for time differentials to show up on the graph. The graph showed that enzymatic activity isn't necessarily affected too much from the pHs of 6 to 8. However, outside those ranges, it began to taper off significantly. So for the temperature graph, ketone 1 was used again, in which they kept all the other conditions the same, however, the temperatures. It was noted that 40 degrees Celsius reached completion of the reaction about an hour earlier than the 30 degree. Researchers also noted the abilities of the high temperatures that the CRED is able to endure, which leads to future solutions to solubility issues, as well as working with higher temperature enzymatic problems. The last experiment the researchers had performed in this paper was to scale up the reaction. They wanted to scale up the reactions to see if CREDs could be used in an industrial manufacturing level. In order to do that, they started a small stepwise increase of the reaction scale from 3 milliliters to 10 milliliters to 50 milliliters to 100 milliliters. Now, they started so small because they wanted to see if increasing the scale size would decrease the intensity of the reaction that has been optimized, as well as it being stepwise in order to study the effects of the vessel size, type, and agitation. Now, they also went up to 250 milliliters, 500 milliliters, and 1,000 milliliters. Since ketone number 2 was making an extremely viscous mixture at 100 milliliters, so thick that the researchers could barely mix it, they decided to lower the enzyme concentration and ketone concentration, which can be seen on the table as it is a lower weight and a lower concentration. This is in order for the 1,000 milliliter reaction scale in order for it to mix and work properly so that everything gets reacted and there's no unreacted material in the end. Originally, the question that the researchers wanted to prove was that can creds be used to make APIs biocatalytically? And they did prove that, as 5 out of the 8 ketones that they had originally reacted. There was one more ketone that was reacted additionally, however, it was due to a heavily modified alcohol dehydrogenase that was turned into a cred. So this is important for future pharmacology because it can open many more pathways to making drugs. It can also lead to many new drugs that are being made from the synthesis of enantiomers that can be seen as analogs for other drugs that have similar pharmacoactivities and different pharmacodynamics. The main question that the researchers had for this paper was to see if ketone reductase biocatalysis could work. And it did. They did make the intermediates they were looking for. They took the ketones and turned them into the chiral alcohols. However, not for all of them, which proves that there's still work needed to be done in this field of research, which they've shown with ketone number 2, and how they had a modified cred from alcohol dehydrogenase react with it, and it ended up working when previously it wouldn't before. One thing they could have performed better on or done to improve this paper, I feel, could have had a larger sample size of drugs and structures so that we could have a better understanding of what bulkiness can stop the reaction from occurring, whether a drug could be too small from occurring, or whether or not it has too many charges from occurring. Also, they could have tried different types of ketones, like amino ketones, such as bupropion HCl or Wellbutrin, which could have led to a larger amount of information gathered, which would make future research much easier.